Up until this point in these linear motion videos, we've been talking about a special case of constant velocity one-dimensional motion. We're still going to be talking about one-dimensional motion in this video, but we are going to broaden our understanding to include objects that are accelerating, where their velocity is not always constant. So we need to define another type of velocity. So we talked about average velocity last video, but we want to talk about instantaneous velocity. So average velocity is over like a certain time period. Instantaneous velocity is the velocity of an object at a given instant. So you're going to have the speed or the magnitude and direction of motion at a specific moment in time. For an object like the ones we looked at last video that has constant velocity, so on a motion dot diagram, your spacing is, if you have equal spacing, you know that means that it's constant velocity. So in that case, an instantaneous velocity is going to be exactly the same as an average velocity. But that's not very realistic. Usually velocity isn't constant. So if we were to model runner A's motion like more how it really is, you would notice that there is a time period here, like 4 or 5 seconds, where the runner is speeding up. Okay, for every 1 second, they have a larger displacement until they reach a point where they're traveling at a pretty good speed and they're running at a pretty constant speed. But then once they hit that 100-meter mark, they're going to slow back down and stop. Okay, so you get not constant velocity in this 100-meter run. Okay, if we were to plot this on a position versus time graph, okay, like we looked at last video, we have down here and up here, we have areas where it's not a straight line. So our definition last time where we used the change in x over the change in t, that's still valid, but it's much more difficult to discern on a graph when you don't have a straight line. Okay, so we can talk about a tangent line. So the slope of the line tangent to this curve at a particular point in time is going to be the definition that we give for instantaneous velocity. The line tangent to a curve, you may remember from geometry, is a line that just touches the curve. So here we're talking about points on this line that are curved. So it would be a line that just touches the curve and is like runs through two infinitesimally close points on that line. Okay. So if we look at 10 seconds here and we wanted to know the instantaneous velocity at 10 seconds, we actually would do it just like we were looking at average velocity, because here we have a straight line, so we can pick a point 2 time points previous and 2 points in the future, and look at the slope of that line. Okay, so there's a rise of 38 meters over 4 seconds. So that means that the velocity for the time point 10 seconds, that runner is going at positive 9.5 meters per second. But when we go down and we look at the time point 2.5 seconds and we try to figure out, okay, what's the instantaneous velocity there? Now we have to work with a tangent line. So we draw our tangent line. Okay, and again, from geometry or from algebra, you've probably talked about tangent lines. You take the limit as that x value approaches 0. So in this case, that's our delta t. Our change in t gets so close, it's just infinitesimally close together, those 2 time points. And we take that delta x divided by delta t with that infinitesimally close. It basically gets the line that just touches the curve. Okay, so once we draw that tangent line, or once we know the equation for that tangent line, we can find the slope of that tangent line. So in this case, it's 36 divided by 7.5 seconds to give us a velocity of plus 4.8 meters per second. Okay, great. So we could actually do this for any time point on this graph. Okay, so I've shown here just an example of going through maybe at a lot of these time points, and we would figure out, okay, what's the tangent line? What's the slope of that tangent line? Okay, that's our velocity. Okay, and when you take calculus, you'll learn that that's actually taking the derivative, and you can get the equation for the velocity graph. Okay, but basically let's say we're looking at all those tangent lines, we find the slope of those tangent lines, and then we plot that. And if we plot that, that's our velocity versus time graph. So for this runner, the velocity versus time graph is going to look like this. The runner starts with no velocity, okay, and then increases their velocity until a certain point, until they reach about 9.5 meters per second, and then they're going to continue on at that pace until they get to the 100 meters, and then they slow their velocity over time until they come to a stop. Okay, so there is a relationship between the position versus time and the velocity versus time graphs. The slope of the position versus time graph is the velocity versus time graph. If you were to plot the slope of the x versus t graph at every time point, you would get the velocity versus time graph. So a fun fact with the velocity versus time graphs, if you find the area under the curve over a certain time interval, you will find the total displacement of the object during that time interval. So let's say we wanted to find out how far that runner went in the first 5 seconds. Okay, so we can use our velocity versus time graph, or v versus t graph, and we're going to find the area of this shaded region here. Okay, the area under the curve. So we know that is a triangle. It has a base of 5 seconds and a height of 9.5 meters per second. So if we take that and plug it into our formula to get the area of a triangle, 1/2 base times height, 1/2 our base is 5, our height is 9.5. Take a look at what happens with our units. So we have 5 seconds times 9.5 meters per second. Well, our seconds are going to cancel out, and they give us just the unit of meters. So we can find, by finding the area of that triangle there, that the runner has gone 23.8 meters in that first 5 seconds. And if we go up and we check our position versus time graph, indeed that's what we see right here. That at 5 seconds, the position of the runner is 23.8 meters. Okay, let's say we wanted to know how far the runner was after 13 seconds. So then we would need to add the area of this rectangle to the area of the triangle. Okay, so this rectangle, it has a side length of 9.5 meters per second, and it has a base of 8 seconds, or a length of 8 seconds. So again, we take the area, so we take 8 seconds times 9.5 meters per second. Again, those seconds cancel, and you're left with just meters. So we can add 23.8 meters to 76 meters, and we get that the runner is at 99.8 meters. Essentially, they're right at that 100 meter mark, pretty much right there. Okay, so that's kind of a handy thing to be able to do with your velocity versus time graphs. Okay, let's think back to last video when we had 2 runners. So we had runner A and runner B, and runner B was running like in the negative direction in the reference frame that we had set up. Okay, so here was our dot diagram from runner B. Runner B was running at a constant velocity. Okay, again, not super realistic, but let's go with it for this example. If we were to make a velocity versus time graph for runner B, then it would be a straight horizontal line at negative 4.5 meters per second. Okay, and if we wanted to find how far that runner went in the first 10 seconds, we would take 10 seconds times negative 4.5 meters per second, and our seconds cancel out, and we get negative 45 meters. Okay, that negative sign you have to keep. So that negative sign came from here because this was negative 4.5, and so it's a negative area, which makes sense because in our reference frame, that runner had gone to the left, which was negative displacement, which is in the negative direction. Okay, so your displacement can also be negative. And that area can also be negative if the velocity is negative. Okay, so that's what I say right here. If the shaded region of the graph is below the x-axis, then the displacement or the area is negative. Okay, so looking at a velocity versus time graph, let's take a note of what things mean. So if we have a horizontal line, okay, that means that between those times, wherever that's a horizontal line, the object has constant velocity motion. Okay, so v versus t, if it's horizontal line, it's constant velocity motion. Here, where I've highlighted, that's not constant velocity motion. The velocity is increasing over time. Okay, so velocity increasing over time. Over on the right side, the velocity is decreasing over time. So that means that in those time periods, so from 0 to 5 seconds and from 13 to 16 seconds for this example, the runner's accelerating. Okay? The horizontal line on the v versus t graph means at that time there's no acceleration. It does not mean there's no velocity. They're definitely moving. They're going at 9.5 meters per second here. Okay? But it does mean that it's constant velocity throughout that time. Okay, if you have a horizontal line. Okay, so looking at our acceleration, so we just said that if the velocity graph is not a horizontal line, if it has a positive or a negative slope, the object is going to be accelerating. So again, with acceleration, we have average acceleration that we can talk about and instantaneous acceleration that we can talk about. So average acceleration is equal to the change in velocity over an object over a certain time interval. So it looks very similar to our velocity equation, except for instead of change in position, it's change in velocity over time. Okay, acceleration is interesting because you have to remember, and this is kind of not intuitive, you have to remember that velocities have a direction associated with them. So yes, an object's accelerating if it's speeding up or if it's slowing down, but it also is accelerating if it changes direction. So even if you're going at a constant velocity through a turn, you are accelerating because your velocity has changed direction. So you've changed part of that velocity, the direction part, not the magnitude, but still you have acceleration if you're turning. So looking at our velocity versus time graph, let's now talk about instantaneous acceleration. So instantaneous acceleration is equal to the rate of change of the object's velocity at a particular time point t. So at a particular time again. So graphically, it's the slope. Acceleration is now the slope of the velocity versus time graph. Okay, so we have a relationship between all three of these graphs that they kind of relate to each other. Position relates to velocity by the slope, and then the velocity relates to the acceleration by its slope. So here, we can use our velocity versus time graph to find our instantaneous acceleration at time point, let's say 3. We're interested in 3 seconds. So here we have a straight line, fortunately, right here. So we can look at the slope of that. We take our change in velocity, which is 9.5 meters per second. Okay, that 9.5 minus 0. Okay, and then we have 5 seconds minus 0 seconds to give us 5 seconds. And we find our acceleration, our instantaneous acceleration at time point 3. It's going to be 1.9 meters per second squared. Okay, that happens to be the same that you would calculate if you were calculating the average acceleration in this case, because it was a straight line right here. Okay, let's say we wanted to look at 15 seconds and we wanted to find the instantaneous acceleration over there. Well, again, we have a straight line here, so we can look at our change in our velocity, which again is 9.5 meters per second. Okay, and then over 3 seconds, because we're at 16 here and we're at 13 here, so that's 3 seconds. So we take 9.5 meters per second divided by 3 seconds, and we get negative 3.2 meters per second squared. Okay, so because these are straight lines, we know that if we found the acceleration at 3 seconds, we know that that's the same for that whole entire area, or that whole entire time interval, not area, time interval here. Okay, and then up at the top where we had a horizontal line, well, the slope of a horizontal line is 0. So our acceleration is just 0 through that whole time period from 5 to 13 seconds. But then at 13 seconds, again, something happens. We start slowing down. We've passed the finish line in this case, start slowing down, and that acceleration is negative 3.2 meters per second squared. Okay, and then right here, we got, now they're stopped, so their acceleration again is 0. Okay, I want to point out that, like, right here, in reality, this is not like a change right at an instant in time. There would be kind of like, this would be curved up here slightly, and then this would be kind of like curved too and come down and connected. But in this case, we're not going to talk about accelerations that are changing. We're just going to talk about like constant acceleration situations. So for right now, just in this acceleration versus time, we just kind of jump from 0 down to negative 3.2, or from 1.9 down to 0, okay, without them being connected. Okay, the last thing I want to talk about is interpreting positive and negative acceleration. I'm going to get rid of this pointer, it bugs me. Positive and negative acceleration. So we use the words in everyday language, speeding up and slowing down, quite often. So let's look at what we need to look at in physics are the signs of the velocity and the acceleration, and how those signs of velocity and acceleration compare. That tells us if an object is speeding up or slowing down. So if an object velocity and acceleration have the same sign, so if it has a positive velocity and a positive acceleration, that means it's speeding up. It's going faster. It's changing its velocity to become faster and faster in the same direction of its current velocity. Okay, or it could be going backwards or in the negative direction in the reference frame, and then have a negative acceleration to make it go even more negative, or having even more negative velocity in the negative direction. And I'm always pointing, I think I'm pointing the wrong way for you guys because it's not flipped. So yeah, more negative. So that's for an object speeding up. An object is slowing down when its velocity and acceleration have opposite signs. Okay, so if an object has a positive velocity but a negative acceleration, then it's slowing down. Or if it has a negative velocity and a positive acceleration, it is slowing down as well. It's maybe backing up, but its backing up is getting slower and slower and slower. It's going to come to a stop. Okay, so that would be an example of negative velocity but a positive acceleration. With that, that's all I have for this video. So thanks for watching, and I will see you in the next video.